Alright, we're going to do a book review today. Hidden Attraction, The Mystery and History of Magnetism. The guy's name is Gerrit Verschuur. Okay, now, these days when I do a book review, I don't necessarily, I just kind of go over pieces of the book that I thought were interesting. I don't really have a really well organized book review like you would normally expect. I'll try to make it more, like a reasonable book review. But when I read a book now, I look for things like, okay, where is the propaganda? Even in a science book, because these major publishers, they don't publish a book if they can't use it to construct a worldview that they want to influence people with. And so they're going to print things that have a certain amount of sort of a mandatory Marxist content to a book. Along the way, we learn many interesting scientific facts, perhaps the most remarkable of which is that lodestone are made by bacteria, a sediment organism known as G5-15 eats iron, converting ferric oxide to magnetic, and over billions of years forming the magnetic layer in iron formations, boasting many informative illustrations. This is an adventure of the mind using specific phenomena of magnetism to show how we have moved from an era of superstition to one in which the theory of everything looms on the horizon. Gerrit Verschuur is a research professor of astronomy at Rhodes College, Memphis, Tennessee. Contributor editor, Air Space Magazine. He writes numerous popular science. So he's sort of an insider, right from there. And does that sound reasonable to you, that you're going to get bacteria to produce that kind of volume of material? That doesn't sound reasonable to me. And of course, I'm a young Earth creationist, so I'm not going to entertain those kinds of long Earth undocumented events. So, okay, here we go. Let's see what this book is all about. Okay. Contents of The Mystery of Magnetism, Clearing the Decks, On the Magnetic Philosophy, Let Experimentation Begin, Oersted and Ampere, The Birth of Electromagnetism, Michael Faraday, Era of Discovery Personified, Fields and Faraday, Maxwell Sees the Light, Heinrich Hertz, Grand Adventure, Curiouser and Curiouser, What If, Magnetic Fields in Space, The Spark That Bridged the Universe, The Error of Creativity, The Wages of Curiosity. Okay, so if one pays attention to experiment and experience, authoritarian beliefs handed down through the generation often begin to feel hollow. This is surely to be expected, since at root beliefs are arbitrary. It is possible to believe in anything you want, and no one can fault you for it. But whether a given belief pertains to the nature of reality is another matter entirely. In this rests the substance of the great divide between science and religion. So right away, starts attacking religion. What scientists may hold, while scientists may hold a belief about the nature of reality in the form of something they call a hypothesis, such a belief is held only until new observations or experience reveal the hypothesis to have been only an approximation of the truth, if not actually unfounded. then the hypothesis will be modified to take into account new information or new experience of one's senses. But a belief can be held quite independently of what an individual's experience may reveal. Beliefs are essentially subjective, mental constructs, and as such tend to act as powerful blinders to the facts of one's experience. For example, it is possible to call it a miracle to survive a tornado that killed one's neighbor and destroyed their homes, but the scientific approach to why certain houses were devastated would depend on observation. It would not take long to discover that the path of a tornado depends on random factors, on chance, good or bad luck, depending on one's point of view, and no amount of belief in miracles could have changed its course. So, right out of the gate, he started, as this attack, science versus religion, which is, I think, a false choice paradigm. It's a false dichotomy. It isn't science. See, he even admits it, sort of. He says they're going to modify the hypothesis. They're not going to trash it. That's the whole thing with the Big Bang, and now you get dark matter, dark energy, expansion, and all this cockamamie arbitrary, because they're really not, the scientific community is not really any more willing to change their minds than any other community. And there's kind of this myth that circulates around science, like it's somehow scientists are superhuman and are not not able to have those weaknesses, and that which is simply not true. At about the same time, in 1269, the first attempts to choose truth over superstition regarding the phenomenon of magnetism took place on a battle-torn field outside the walls of the besieged city of Lucera in Italy. In those dark days, when men did little but fight other men for the right to control what people believed, Lucera was under siege for the third time in 14 years. A crusade had been launched against the people, the Crusades being the polite name given to wars sanctioned by the papacy against anyone believed to be the enemy of Christianity. As a reward for being involved in God's work, the Pope was wont to hand out the title Peregrinus, which means pilgrim, and thus Pierre de Maricourt, of unknown birth date, became Peter Peregrinus. Okay, isn't that what's going on today? There's a group of scientific elitists that want to control the world. It's like there's so much hypocrisy in these books. None of this stood in the way of his writing a book about his wondrous discovery. It was dedicated to the Right Worshipful Master William Burrough, Comptroller of Her Majesty's Navy, and Norman offered his secret humbly, hoping that it would benefit many. Because the secret was contrary to what had been believed up to then, Norman, who described himself as unlearned mechanician, I guess we would call it mechanic, unlearned mechanician, was more than a little worried about the consequences of publication. Revelations of nature's truth had not always met with applause. That remains true to this day. Witness the continuing reaction to the notion of evolution. On the contrary, excommunication, torture, and general discomfort on fiery stakes were hazards faced by many of those whose thinking did not conform to established dogma. This is great. It's supposed to be a science book, right? Okay. Although I guess he's getting into a little bit about, the philosophy. I got to get. I always take out my things as I go, but maybe I'll have to leave them in. My little bookmarks. Okay, let's see here. Moving on ahead. This won't take too long. I'm jumping through this book pretty quick. London physician was not to hold back once he had seen the light, and now, through philosophers and of the vulgar sort, imagine with an absurdity unspeakable that the whole heavens and the world's vast magnitude are in rotation. He wrote, but that didn't explain why the earth rotated. In the search for an answer, he gave thanks to the Creator for having set it up this way. Hardly a scientific answer. But because the earth had two poles, like the lodestone, he could imagine that it had a natural axis in space, a north-south alignment, verticity he called it. Then all you had to imagine was that some cosmic magnetic force pulled on the earth to cause it to spin around the axis. I think there's certain things that aren't going to be, that aren't explainable, such as the rotation of the earth. You know, when you're growing up, you get this accretion disk theory of how planets form and so forth. It's not tenable that you can't. The forces of repulsion of the materials are greater than the gravitational forces. So you would never get anything like that to happen. You got the problem, of course, with the moon and all the exactitude of the moon and the size, the replacement, and so forth, that defies some kind of natural explanation. But the wonderful wisdom of the Creator, therefore, forces were implanted in the earth, forces primarily animate, to the end the globe might with steadfastness take direction, and that the poles might be opposite, so that on them, as at the extremities of an axis, the movement of diurnal rotation might be performed. Now the steadfastness of the poles is controlled by the primary soul. And actually, that's not a bad statement, because you can't get anything without God first. You wouldn't have one hydrogen atom, because you need a pre-existing reality before you can get the universe we have. That's why, you know, scientists are all saying, well, to ask what happened before the Big Bang is nonsense, or something like that. That to me, if you're not going to answer that question, then you're useless. You know. Based on experiments with Torilla, Gilbert thus reasoned that if the Earth could be moved so that its axis pointed away from north, it would inevitably swing back to its correct alignment. The mystical magnetic influence that he had done so much to rescue from the maw of superstition would then cause the earth to point again towards Cynosura, the key direction, the center of attraction associated with Ursa Minor, specifically the pole star Polaris. In other words, just as the lodestone floating in water would align north-south, the earth floating in the air, as it were, would also swing to align north-south. This notion that the earth's magnetism was linked to the heavens set a bandwagon rolling down the avenue of human thought for half a century. And it does make that, and see, that makes a little more sense. You have, because if you think of it, why is, you know, the earth is in a rigid orbit. It doesn't wander off, you know. And it seems like you need electromagnetism, not gravity. All the gravity, I think, could be properly understood as residual van der Waals forces. Kepler and Galileo found the magnetic concepts of great use in their own struggles to understand what kept the planets in orbit. Kepler said so explicitly when he wrote that he had placed a celestial rooftop upon the magnetical philosophy of Gilbert, who himself had built the terrestrial foundation. It all fitted so well that members of the opposition, many of them clerics struggling to reconcile Galileo's heretical claims with the teaching of the Bible, were forced to take a different approach to rescue the dogma from extinction. The thing is, the Bible never argues for a geocentric universe. The expressions of the sun rising and sunset, we still use them today. That's, the Bible uses a lot of everyday language. It employs all of the grammatical and linguistic patterns of everyday life. It's not some kind of textbook of math and so forth. I mean, it does have math and science in it, but it's not written in a dry fashion like this. There's so much going on there with historical narrative, poetry, prophetics, apocalyptics, and so forth, that you get a lot of everyday language in the mix. Bennett had pointed out that Grandami claimed his magnetic proof of the Earth's immobility was rooted in physical and moral truth. Yet the moral of our story is that when one uses beliefs or cherished dogma to account for nature's wonders, one is inevitably led up the garden path and left with nothing, not a single idea that can stand the test of time, if for no other reason than the original ideas that give rise to the dogma were fictitious of human imagination to begin with. They were fictions because they were not founded on observations of nature under experimental conditions. It was here that Gilbert's work stood out so massively, even if his interpretation of his observations often left much to be desired. He made observations that revealed certain qualitative patterns in regard to the nature of the forces existing by lodestone. Little did he know that it would be a century or more before the necessary quantitative aspects would be added to observations, a factor absolutely necessary before anyone could begin to probe beyond nature's appearances. Let's see, what did I want to say about this? There are certain things you can't observe in the history of the world. This is not like something that he's talking about there that is not a universal dynamic that can be applied. And the more we learn, the more it becomes evident that there's necessary pre-existing intelligence. Okay. The 17th century marked a move away from reliance on superstition, outdated beliefs, or biblical myths for natural phenomena. The transition is not yet complete. That is why fundamentalists still struggle with the facts of evolution. Oh, that's great. Yes, it is very difficult for the human mind to accept a new truth, especially one that transcends a long-held belief. What happened back in 1600 or so was that human beings began to seek answers to their questions by confronting nature directly. Above all, they paid attention to the truths, facts revealed in experimental situations. This approach was completely at odds with the ancient technique finally honed over thousands of years that relied on verbal argument to prove a point without heeding the messages found in natural phenomena. and certainly not by relying on experiment. In the specific case we have just considered, Martha Baldwin put it this way: Verschuur saw in the novelties of Gilbert's and Kepler's magnetic astronomies an intolerable temerity of the human mind to limit divine omnipotence and to claim to know fully the ways of God. But that is precisely what has been going on ever since scientific questioning has led to discoveries that set limits in areas where ardent believers used to picture God as capable of anything. If there is one thing that scientific quests have turned up, it is that there are natural laws that determine what is possible and what is not possible in our physical universe. This would suggest that if God should any such entity exist, created the laws, God would surely be as subject to the laws as anything else in space or time, which I would like to argue is not true, because if you're going to position a God who created the universe, he has to be outside it and has a lot much more capabilities and can, in a sense, do what seems to be breaking these laws, but he's not breaking laws in his own reality, in the greater dimensionality. Despite the shortcomings in magnetical philosophy, Gilbert was a pioneer in showing a new way to proceed to uncover nature's deepest secrets. The road ahead now lay wide open. The quest would prove to be a long one. Even if Gilbert had overestimated the usefulness of his interpretation, his insights revealed the presence of order in what had for so long appeared to be a chaotic world. If nothing else, that is what science is all about: recognizing order in a world of phenomena and extracting from that order expressions of underlying laws that account for the way things are. So, the laws, this whole idea of laws is questionable in the sense that they're parameters that God set to create a universe for finite beings. The idea that I think that the implications of calling it laws are not right. But at any rate, nevertheless, Ampere's personal misery had an important effect on his intellectual development. Tossed back and forth between a world in which he sought truth and stability in the unearthing of the laws of science, as opposed to the real world in which chaos and confusion appeared to reign supreme. He also struggled to reconcile his strong religious faith with reality. He always sought certainty, and that such determined the evolution of his scientific work. For example, for Ampere, it was important to accept both the existence of God and the existence of the world of external reality with which his scientific questions had forced him into head-to-head contact. The two seemed irreconcilable, one rooted in faith, the other in fact. His way out of the dilemma was to find inspiration in the writings of Kant, whose philosophy made it possible to retain a religious faith in the context of living in a universe that appeared to function rationally. This helped Ampere deal with inconsistencies of life. So, oh man. Okay, first of all, there's a big problem with trying to juxtapose fact and faith. Because if you read the Bible, your faith is expected to be based on facts. That's the whole thing. Read the Bible. If you read the Bible, you see over and over again, God refers to historical events. In fact, the one thing God says about himself the most in the Bible is that he led the children of Israel out of Egypt. That's his most common identifier, and which is a historical event. See? How my Faraday managed to do so was largely guided by his personal approach to quest, which was defined by his religious outlook on life. See, this is what I'm saying. Now the guy has to admit he knows Faraday is hard to portray Faraday without being kind to his religious outlook on life. He was another of the major figures in our story who were imbued with Kantian metaphysical belief in the unity of forces of nature, but to him it was more than that. His religious upbringing within an obscure Christian sect called the Sandemanians led him to apply what he learned in his church to his studies of nature. Sandemanians lived their lives according to the Bible and in imitation of Christ's perfect thoughts and deeds, but with a difference. There could be no intermediary between them and the Bible. In the Sandemanian sect, the Sandemanian sect, there were no clerics to act as interpreters of the written word. The alleged source of truth, that's what he got, the alleged source of this. Oh my gosh. And he didn't even put that in parentheses. They taught that to find the truth, all you need to do was to look carefully and closely enough, and you would see it for yourself. No one could help anyone else do this. Once the truth was seen in this manner, the interpretation could not be argued, and that was how Faraday approached nature. He learned to confront nature directly. In that way, he would learn her secrets, in particular those related to the unity of forces. Faraday discovered nature's laws by direct observation and experiment, not by listening to what theoreticians said he should find. For him, this left very little room for mathematics, which could not help anyone actually see more clearly. Mathematics might help others to describe what was found after the fact, but it appeared to serve no purpose in guiding the search any more than a cleric could help one discover what was written in the Bible. For Faraday, the truths of nature were there to be observed directly with no intermediary, such as a college professor, to tell him how to look and where to seek. To make progress, all the dedicated researcher had to do was learn to see clearly. That Faraday was able to do better than almost anyone else in his time. So this is really interesting. I attend a church something like this, where it's a house church. We have no clerics. Everybody is sort of expected to know the scripture pretty well, and that's why it works, because everybody there is pretty well versed in the scripture, or they're getting to be that. And that's the way this works. And we're learning some other things, like how to let Jesus guide you daily and minute by minute, as opposed to sort of having some kind of formulaic approach to life. And so that's pretty interesting. We have sort of that in common with Faraday. Faraday was a little bit of one of these he had the kind of a strangeness in terms of his intuition was incredibly sharp, like Tesla. Nikola Tesla seemed to have a similar kind of intuition. It seemed like it was coming from another world. It was very bizarre. How and why Faraday managed to do so was largely guided by his personal approach to quests. Oh yeah, we read that, didn't we? Yes. Okay. All right. So I'm not really, as you notice, I'm not really getting too much into the actual science of this too much, because I'm just looking for the key passages of the worldview kind of things. So progress in the study of magnetism and electricity was always able to move forward swayed by the cautious of clerics or theology. Nowhere in any of the world's fundamental religious tracts were there statements about the nature of magnetism. This meant that physicists did not have to struggle against church doctrine, as was Galileo's lot when he tried to show that the sun at the center of the solar system. No segment of the population was offended by discoveries about the nature of magnetism in the way that religious fundamentals continue to rankle at the discovery of biological evolution. That always cracks me. This freedom to explore beyond any possible restraints placed on pursuing certain other questions may account for the rapid progress in physics that took place in the 19th century. This is not to imply that physicists involved did not hold religious beliefs. We have seen that many of them did, only that these beliefs did not hamper progress. In the case of Faraday, they helped. So they can help, and actually there is an allusion to magnetism in the scriptures when it speaks of God holding all things together. And I mean, electromagnetism is it's the force that constructs atoms. The electric charge and so forth. And by the way, scientists can't even tell you what an electron is made out of. So, the arrogance to think that they got so many answers, and it's all they're wrapping it all up. Ampere, whom we have already met, was a fascinating example, although his personality and approach to science were ideally suited for taking major steps forward. His psychological state prevented him from making more progress than he did. He was guided by theoretical expectations to search for specific phenomena. These he expected to observe. On one occasion, when nature had offered him something different, he could not see it. This reminds me of CERN, going to look for the Higgs boson. They came up with something that is supposed to be the source of mass, but itself has a mass. So, it's not very explanatory, if you ask me. Anyway, so here's that situation. This occurred in 1822, 9 years before Faraday discovered induction. Ampere performed a series of experiments that produced unexpected results that historians now realize were unequivocal evidence for induction. But to Ampere, the effect, although noted, was simply ignored. It was not what he was looking for, and he failed to recognize its significance. What our brains are capable of perceiving in the behavior of nature is heavily determined by what we are ready to see, and perhaps more importantly, by what we expect to see. This is a hazard all scientists confront, one to which most of them assume they are immune. But when experimenting at the borders of the unknown in search of a particular phenomena they might cast light, our unconscious dependence on theories on how nature behaves makes the path of progress rocky. That's probably the best paragraph in the book. This is so. I want to read this again, and by the way, this applies to all different areas of life, not just the science. Even your search for God and search for God's will and so forth is subject to these same faults, and so you got to be careful. This is what our brains are capable of perceiving in the behavior of nature is heavily determined by what we are ready to see, and perhaps more importantly by what we expect to see. We're always talking about this at our house church. This is one that comes up every day, every time we meet. This is a hazard all scientists confront, one to which most of them assume they are immune. But when experimenting at the borders of the unknown in search of a particular phenomena that might help cast light, our unconscious dependence on the theories of how nature behaves makes the path of progress rocky. And scientists also do this by automatically ruling out a divine intelligence, prime mover, and so forth. Faraday was a scientist more likely to explore the unknown for the sake of exploration than to perform experiments to test theories. He was not only willing but uniquely able to proceed without any theory or beliefs in mind. For that reason, Faraday became known for discovering electromagnetic induction, the same effect seen but overlooked by Ampere 9 years before. Although Faraday thought he could see field lines when iron filings were sprinkled over magnets, those lines were actually fragments of his imagination. All he had to do was to tap the paper on which the filings rested to see that they moved until they all congregated at the poles of the magnet. Nevertheless, this fragment turned out to be a powerful concept for understanding the nature of magnetism. If one wanted to know where the fields originated, well, that was another story, quite unrelated to the physics of fields. In other words, fields should be considered a distinct entity with certain properties, no matter how mysterious they might at first seem, and the mathematical models that were to emerge from these insights changing the field strength in an equation became a simple matter. The field was a parameter to be manipulated, whatever its origins. And by the way, I think he's wrong to say that this tapping the paper erases, in a sense, the reality of the field line, because what you're doing, in a sense, okay, the further towards the middle of the line, the weaker the forces. So it's like tapping something down the steps, that's all. I mean, the field line is still there. It's just when you get the filing out of the frictional inertia situation, is going to move to the strongest pull near it, which pulls it up. Eventually it goes up towards the pole. It doesn't eliminate the field lines. I'll talk about field lines more in this conversation, this book here. Okay. Those of us who are not as purely directed by an idea in which laws are unfolded as a result of experiments may tend to guide our preconceptions by unconscious drives that send us in those directions where we hope to find the truth. We prefer to look at a lost key in the light of a street lamp because it is brighter there, not because that is where we lost the key. Faraday was not such a person. He searched where nature taught him to search. Paradoxically, he wrote that there is no natural philosophy in my religion. One commentator noted Faraday's science, particularly his detailed research, seems so independent of his religious beliefs, yet he clearly mixed religion and philosophy. To him, they were inseparable. For example, he believed that the term used to describe experimental results should be theory neutral. His religious feeling and his philosophy could not be kept apart. There was a habitual overflow of one onto the other. This directly reflected the Sandemanian credo that he should have no intermediary in regarding the Word of God. No cleric should stand between him and the words of the Bible. And I would add, no priest should be standing between you and the God who saved you. No cleric should stand between. No theoretician's hypothesis should come in the way of experiment if he sought to determine the nature of truth in the physical universe. In a letter to William Whewell, Faraday went on so far as to state that promulgating one's theoretical views under the form of nomenclature, notation, or scale actually retards the progress of science. He was in pursuit of the laws of nature, which his religious upbringing led him to expect must exist. He was searching for God's laws in nature and became uniquely able to see and recognize the manifestation of those laws more clearly than anyone before him. Although nature's book lies open for all of us to consider, what can be apprehended directly is often subject to distortions introduced by poor vision or is lost in translation. Let me see. This is really interesting because all science should really be called the study of God's creation. How did God do it? This is what we're really trying to apprehend here. Faraday was driven by a pure urge, a lofty idea that remained unfettered by formal university training, which might have forced him into a more conventional mold. He was the right man at the right time, doing the right things at the right place. To understand magnetism and electricity, he approached the phenomena head-on, without any preconceived notions to misguide and blind him to what might be revealed in his experiments. Today it would be impossible for Faraday to emerge from an uneducated background and rise to a significant level in the world of science, given our system of education and the way scientific research is done. The establishment, our highly formalized educational system, will prevent an amateur such as Faraday from entering. Also, the structure of modern science is heavily slanted toward a grounding in theory, which involves learning how to manipulate concepts in mathematical form. I have observed that the system does little to encourage creativity. It does even less to encourage the support of experimentation of the type Faraday was so good at. The modern graduate student in the United States cannot expect to plunge directly into an exploration of nature's secrets without having been thoroughly indoctrinated into how to perform experiments. This is in large part because experiment that is used nowadays is vastly more complex than anything Faraday could have dreamed of. A modern Faraday would have to approach nature with his or her insight heavily laden with expectations gleaned from lectures. This is generally regarded as a good thing. Viewed from the historical perspective, we wonder whether that is necessarily true. Perhaps there is some intermediate way. Faraday explored nature directly and learned to see more clearly than most others. It is different now. Although science is making huge strides in all disciplines, progress occurs only in the context of expectations that are drilled into students from the start of their studies. As a result, scientists appear surprised when they stumble onto new phenomena. But why should they be surprised? I can't help wondering whether Faraday was ever really surprised by what he found. He was surely awestruck, but was he ever totally taken aback? So there's another good, I think, a good couple paragraphs there. Yeah, it's interesting how indoctrinated things get, and I guess, this just makes me kind of, like, hey, how come he's not allowing people to apply this to the indoctrination of evolution? So, okay. At about the time Faraday was conjuring up notions about the existence of fields, James Clerk Maxwell was born in Scotland of a comparatively well-off and highly cultivated family. Before he died at the age of 48, he made marvelous use of Faraday's insights and transformed physics in the process. Maxwell set the study of magnetism and electricity on a solid foundation for which it would never be toppled. By age 3, Maxwell exhibited a precocious curiosity by exploring the bell wires that threaded their way through the old mansion in which he grew up. Whenever he wanted to know the answer to some specific question, he would ask, "What's the good of that? What's the go of that?" Okay. Perhaps reflecting the notion that if one explored long enough, one should be able to find where the trail of mysterious wires led. Should the answer not satisfy him, he would insist, "What's the particular go of that?" Maxwell's nickname at school was Dafty, a boyish put-down referring to his appearing eccentrically, silly, or dumb. To those who suffer similar humiliation as a child, there is solace to be found here. Of all the children who attended the school in Scotland, the Edinburgh Academy, only Maxwell's name will live long in the annals of civilization, although this is little consolation while one is alive. A biographer later said that Maxwell was not readily fobbed off with dogma, stories, or myths. He maintained a simple Christian faith that gave him peace too deep to be ruffled by bodily pain or external circumstances. Perhaps this independence of spirit also made him relatively impervious to the opinions of his youthful peers. And by the way, this guy, let me turn my heat off and get a little warm and nice spacey. By the way, the guy that's writing this book, should appreciate that there was Christianity had opened up minds to optimistic approach to life. I'm watching this really interesting lecture series by an Eastern Indian fellow. He's a scholar and a missionary who is giving a series of lectures, Does the Sun Have to Set on the West? And he's going into great lengths presenting a case for the prosperity of the West as it pertains to the philosophy of Christ. And so this is what we're seeing with Maxwell and Faraday and a lot of these early pioneers was the fruit of the Reformation, of exposing people to the actual words of God that they can read for themselves. At the age of 14, Maxwell published his first scientific paper on how to draw a perfect oval with a loop of string moving about 2 fixed points. Halfway through his school courses, he underwent a sudden change of personality. A schoolmate reported that after years of shyness, he surprised his companions by suddenly becoming one of the most brilliant among them, gaining prizes and sometimes highest prizes for scholarship, mathematics, and English verse. In our book, we cannot present a fair summary of a man who studied color vision, discovered the fisheye lens, determined the nature of Saturn's rings, explored statistics and the physics of molecules, and dabbled in engineering. We will attempt only to communicate the essence of his great work, the formulation of a series of equations that summarized all there was to know at the time about electrical and magnetic fields, a formulation that would set the scene for the academic discovery of radio waves. Soon after graduating, it was the formulation that would set the scene for the accidental theory of radio waves. Soon, graduating from Cambridge University in 1854, Maxwell began his monumental work on the persistent mysteries of the nature of magnetic and electrical fields by trying to clarify for himself what the problem was about. To proceed, he needed to summarize exactly what was known so that he could then begin his own journey along the path toward greater understanding in principle. This is what any good scientist does. In due course, his insights would provide an entirely new world to human gaze, a world that lay behind all the peregrinous Gilbert, Oersted, Ampere, and Faraday had groped at but could not fully comprehend. Maxwell found and opened a window on the nature of the physical universe that showed rolling scenery stretching to the horizon, scenery of unparalleled beauty and elegant simplicity. If one learned how to keep to the window and look out, one could also soak in the view and obtain personal enjoyment from it. The depth of Maxwell's discoveries, as well as the work of dozens of physicists who came after him, is well beyond the scope of this book. Nevertheless, we can get an inkling of the beauty of the world he found by considering a few highlights. I will try to unveil that vast world beyond our senses, even if we cannot all roam that world beyond appearance, a world that is the essence of the physicist realm, a world that requires a passport in physics to enter it and explore it at will. When Maxwell arrived on the scene, he did not have to contend with the morass of uncertainty which Faraday did so much to clear up, and the way was more easily opened for the key ideas which Maxwell supplied. Faraday had already done the experimental work, and Maxwell, who was to construct the theory, never failed to recognize the value of the contributions made by the gifted amateur of the Royal Institute. Oh, am I still reading? No, but I don't have my go point. Oh, no, I do. Okay. Okay. The notion of a field of potential allowed for more possibilities than a simple view of action at a distance, which we have discussed before. Action at a distance implied the presence of physical connections between a magnet and a piece of iron, which allowed contact over a distance to be made like a row of dominoes tumbling down to let one under the iron rod know about the presence of a magnet at the other end. But how did the field propagate in empty space or through intangible air in the room? The natural explanation was to invoke the existence of an ether that filled space so the action could propagate through it. But Maxwell's work would ultimately lead to the rejection of the ether hypothesis, which I think is an incorrect interpretation. It doesn't. You have to. Okay, you have to have some kind of ontological reality. You can't just chalk it up to a mathematical model. That doesn't explain anything. That's look. We've learned a lot more about space since Einstein, and I don't reject Einstein's ideas about, and they're not all his ideas, obviously. He shared these ideas. There's a lot of other people at the time who had the notion of properties of space, even the vacuum, and there's something giving that space, the distance between the magnet and the iron. There's something given a characteristic. It's not just a mathematical equation floating in the air. Right? Maxwell approached his study not by considering what others well-versed in mathematics had written, but by turning to the words of Michael Faraday, who seemed to be using a language quite different from mathematics, yet his description had come closer to the nature of reality. This caused Maxwell to write, "As I proceeded with the study of Faraday, I perceived that his method of conceiving the phenomena was also a mathematical one, though not exhibited in the conventional form of mathematical symbols. Faraday's tremendous insights awakened Maxwell's imagination. Faraday, in my mind's eye, saw lines of force traversing all space, where the mathematicians saw centers of force attracting at a distance. Faraday saw a medium where they saw nothing but distance. Faraday sought to see of the phenomena in real actions going on in a medium. The mathematicians were satisfied that they had found it in a power of action at a distance impressed on the electric fields. Faraday's conceptual leap had left others gasping, at least those who were aware of it. It is perfectly natural for us to consider the interactions between objects involve touch, for that is within our daily experience. I cannot move something without physically touching it. As a result, I believe that this is natural. Nature, however, does not necessarily function in a natural manner. This is where Faraday was able to separate himself from the bias introduced by everyday experience. That was his creative steps. It is in this way, by considering a totally new point of view, that problems are often solved. Maxwell realized that Faraday had begun by seeing the whole, a concept of the phenomena viewed from a distant perspective. In so doing, Faraday was able to recognize the parts. Mathematical methods, on the other hand, began with the parts and tried to reconstruct the whole. Maxwell was so excited by reading Faraday that he advised all students of science to read the original memoirs on the subject. For science is always most completely assimilated when it is in its nascent state. How true this still is, and how impossible it has become to follow Maxwell's advice. Unfortunately, to approach the subject with the state of mind of the pioneers is not an efficient way to learn in order to graduate in a university course. Even for the likes of Faraday and Maxwell, it took decades to come to the understanding they struggled so hard to achieve. New generations, if they wish to make progress, cannot afford the luxury of going at such a slow pace by starting all over again. Modern textbooks on electricity and magnetism cannot afford the space to consider the point of view of historical figures. As a result, university courses are impoverished through the loss. The great sense of adventure felt by the pioneers of science thus becomes remote. Faraday was aware of Maxwell's efforts to formalize what Faraday had found in the laboratory. He recognized in the younger man's kindred spirit, even if the two of them appeared to operate in different modes. Many people interested in science have found the mathematics daunting, and they will relate to what Faraday wrote to Maxwell in 1857. We have quoted this before, but to do so again makes the point. When a mathematician engaged in investigating physical action, the results has arrived at his conclusion. May they not be expressed in common language as fully, clearly, and definitely as in mathematical formula. If so, would it not be a great boon to such as I to express them so, translating them out of their hieroglyphics, that we might work upon them by experiment? Faraday felt that Maxwell had managed to convey something of the spirit of his insights in a way that he could understand. I've always found that you could convey to me a perfectly clear idea of your conclusions, which, though they may give me no full understanding of the steps in the process, give me results neither above nor below the truth, and so clear in character that I can work from them. He begged other mathematicians to translate their results into a popular, useful working state, a cry from the heart to which so many laypeople interested in science can still relate. Maxwell took what he learned from Faraday and tried to generalize the picture. He began with the mental models and experimental results, and after he had found the truth underlying surface appearances, he was able to discard the mental scaffolding. What he was left with was his set of beautiful equations. By 1873, these were available for all to see and use. Not everyone interested in and capable of understanding them agreed on their relevance. However, the community of scientists was divided into two politically oriented schools: the British, Maxwell's point of view, and the Europeans, which clung to the notion that electrical magnetic forces were central and that physical contact through some intervening luminiferous ether instantaneously carried force from point to point, action at a distance. And by the way, that argument's still going on, and I don't think they're really all that mutually exclusive. I mean, if you can have elements of both of them, and you probably, if you had eyes to see in greater dimensionality, there wouldn't be any kind of disconnect. Maxwell's discovery of a set of equations that described the nature of magnetism, electricity, and light in one fell swoop, and their successful marriage heralded the discovery of other electromagnetic waves. His equations provided the resolution to the question asked when someone found the first piece of lodestone and noticed that it attracted fragments of iron without touching them. Why? I don't know if it didn't really answer that too. I mean, when you get into atomic theory and electrons and stuff like that, then you get a little bit more. You get a little bit more answers, but not even that's very incomplete. Because, like I said, we don't know what an electron is, and we don't know really what a charge is, and we don't know how charge travels. I mean, I guess you could say, well, a wave, but a wave of what? A wave of what? A wave of equations? Force fields contain a certain amount of energy that can be directly sensed by our nervous system in the case of light and heat, or detected by experimental apparatus in the case of other forms of electromagnetism such as radio waves, ultraviolet, X-rays, and gamma rays. Although the energy contained in a light wave is trivial by comparison with physical actions such as closing a door, it is enough to cause a reaction when the light wave strikes the retina. The modern explanation for such electromagnetic radiation is more peculiar still. All forms of electromagnetic radiation can be treated either as a wave or as a particle. If light is a continuous stream of particles, as Isaac Newton imagined it to be, the problem of how it travels from point A to point B is easy to deal with. Obviously, particles can travel through space. No carriers are required, no ether, because the particles just zip right along. The particle point of view avoids the problem invoking a medium through which waves have to travel to traverse space, empty space. Yet both the wave and the particle concepts are useful. The important point to bear in mind is that the energy of electromagnetic field is carried by means of a particle or a wave, depending on how you look at it. See, to me that just means that what makes the electron or the electronic wave, the electromagnetic, is derived from greater dimensionality, and we're just experiencing a part of it. After Hertz discovered radio waves, he showed that they traveled around his laboratory at the speed of light, both in the wires in his apparatus as well as through the air. In principle, he could have done an experiment to show the photon, a term used for all electromagnetic particles, even if they are not related to light, were involved. In practice, to do so would have been beyond his means. Now let us return to our original question. What is magnetism, and why is there a distinction between electromagnetism and plain old magnetism? If the underlying force that links electricity and magnetism is electromagnetism, why do we observe what appear to be two distinctly different phenomena, electricity and magnetism, in everyday life? The answer lies in the way we perceive or experience these two forces. In the theory of electromagnetism, electricity and magnetism are two aspects of an all-encompassing force, one phenomenon. Under normal conditions, they are so intimately linked that we cannot speak of one without the other. In the parlance of physics, they are said to be symmetrical. If we look at an electromagnetic wave from an appropriate point of view, such as is defined by mathematical description, for example, the symmetry is perfect. To discover that an electromagnetic wave consists of two parts, you have to destroy its cohesion, that is, break its symmetry. Consider a perfect apple. If you want to learn about the apple, you might take a knife and cut it in half. Now you have broken the apple's symmetry, and each half, while resembling the other, is no longer symmetrical in the way that defined the unblemished apple. Instead, you have two halves, which may look alike, but the perfect apple no longer exists. Your curiosity about the apple destroyed its perfection. Even if you push the two halves together again, you cannot restore the symmetry that existed when the apple still hung on the tree. In recent years, well, in a sense, you restore sort of the appearance of the symmetry, because now, if you're able, put the two halves together and hold them together, you spin it around, now it has the original symmetry. But at any rate, in recent years, physicists studying the nature of the forces and particles in the universe have explored in great detail the concept of symmetry. It turns out that they can describe the nature of electromagnetism in terms of equations that exhibit symmetry. Under certain conditions, that symmetry is broken and gives rise to electricity on the one hand and magnetism on the other. When does symmetry break? The answer depends on who is asking. In nature, the act of touching or of directly perceiving destroys the symmetry of the phenomena you wish to study. To touch is to destroy. However, this does not prevent physicists from constructing an accurate picture of what the aforementioned apple must have looked like before it was cut. This is the case for electromagnetism. Electromagnetic waves from the sun and from radar, radio, and television transmitters exist in space around us. When solar radiation strikes our hands, it is felt as heat. When sunlight strikes our retinas, it is sensed as light. When radio signals from a nearby transmitter enter the antenna of our television sets, we can see a picture on the screen. In all cases, the symmetry of the original electromagnetic field is broken in the act of perception. One side of the symmetrical coin, the electrical aspect of the wave, in these examples produces a change in our cells or in the amplifier of the television set. The electromagnetic wave from the transmitter triggers a wave in the antenna, and its electrical component is detected and amplified by the electronics of the receiver to produce the sound and picture carried by the signal transmitted from the television station. Similarly, it is the electrical nature of the electromagnetic wave called light that we experience through the mediation of our eyes as sight. The act of seeing the light breaks the symmetry of the electromagnetic field at your eye. So what, you may ask, what does all this have to do with the question asked by William Gilbert and Peter Peregrinus, what is magnetism? The new answer is that magnetism is the phenomena manifested when the symmetry of electromagnetic force is broken. The same symmetry breaking can also produce electricity. It depends which aspect of the broken symmetry you study in an experiment. To have a static magnetic field such as is produced by a lodestone, symmetry is already broken. If you dig down to the molecular level, you'll find movement of the form of tiny currents giving rise to the magnetism. Those are not alternating currents such as are involved in producing electromagnetic waves. They are direct current that perpetually flow in one direction in small loops. Oh, by the way, where does that energy come from? Scientists don't know that either. It's a perpetual motion machine. Thought they weren't supposed to exist. Direct currents are not symmetrical. They flow one way only. Symmetry would require that they spend as much time flowing in one way as the opposite direction. If they do so, you have an alternating current, and it immediately radiates electromagnetic waves. If the electrons inside some substance were all rushing around randomly, the net magnetic field produced would be zero. A single particle moving in a circle would produce a field, but unless the particles move in an organized fashion, their contributions to a net static field cancel out. If we set up an electrical circuit and use a battery to send currents flowing one way only, we have defined a direction. A single direction is not symmetrical. A current that alternately flows one way and then in the opposite direction and does so regularly is symmetrical and is able to generate an electromagnetic wave that travels through space. The frequency at which the current changes direction determines the frequency of the radiation. An FM radio signal received at 100 megahertz on the dial is produced by electrons rushing back and forth 100 million times per second in the transmitter. In the case of Hertz's experiment, he inadvertently produced radio waves at a frequency of about 30 megahertz. The power in electrical outlets in the United States homes arrives at an alternating frequency of 60 hertz, which produces electromagnetic waves with a wavelength of 500 kilometers. The notion of symmetry finds its roots in elegant and beautiful equations used to describe electromagnetic waves. But why does the force of electromagnetism exist to start with? How did it come into being? Experiments and theory have shown that under conditions involving very high energy, found only in particle accelerators in the early universe, two of the four forces, electromagnetism and the weak nuclear force, were one. Electromagnetism and the weak nuclear force wants a unity, two aspects that we call electroweak force. The properties of electroweak force were theoretically predicted and then observed in particle accelerators experiments, in which matter is smashed together with such violence that energy conditions similar to those in the early universe, which is, nonsense anyway, are duplicated. Under such conditions, the electric weak force was wrapped in symmetry. Such experiments allowed the properties of the force to be measured, and they fit the theory. When the universe was only 10 to the negative 12 seconds old, 1 trillionth of a second, it was very hot and very dense and filled with energy. This is a whole Big Bang thing is so bogus, but at any rate, back then there was no electromagnetic radiation, no light, no heat, or X-rays. Instead, the electric weak force existed. It had within the potential to create two forces, the weak and electromagnetic force, but that could happen only after the universe cooled as it aged beyond 10 to the negative 12 seconds. Then the symmetry of the electroweak force was broken, and the two sides of the electroweak force became manifested, one acting over a very short distance, the weak force, and the other over great distance, electromagnetism. The weak force resides deep within the nucleus of the atoms and is important in controlling how bits and pieces of radioactive nuclei are held together and break apart. And because the electromagnetic force acts over vast distances, we can see stars at night. And I have a problem sort of with the electric weak, the whole thing of half-lives and so forth. I think that we're looking at something that's derived. At any rate, symmetry breaking is something like a phase transition that occurs when, for example, water is cooled enough to turn to ice. In the liquid state, the water has certain properties and no preferred direction. It is symmetrical in a sense. But ice is crystalline and has a clear structure, which is not symmetrical in the sense that water is. The symmetry that existed in the liquid state is destroyed when water turns to ice. Cooling in the early seconds after creation of the universe caused the two sides of the original cosmic coin, the electroweak force, to become manifested as electromagnetism and the weak force. These continue to exist independently forever, as they do to this day, 15 billion years or so later. This discussion does not imply that all the electromagnetic radiation we now observe was created when the universe began. Instead, the laws of physics that describe electromagnetic phenomena were laid down in the first fraction of a second of the universe's existence. Similarly, the laws that determine the action of the weak force were created at that instance. Before then, neither the weak force nor the electromagnetic force existed. In other words, when the universe was very young, hot, dense, the laws of physics were different. More specifically, the nature of symmetry was such that electromagnetism and the weak force had not yet parted company. And this is so speculative. Why do you have to have that pre-existing condition? And it's what do you call it? Antimony. It's stronger than paradoxical. It's oxymoronic. That. Infinite density. There's these pre-existing conditions that are not, the people that are coming up with them are coming up with what non-scientific. It doesn't. It's like, I don't know. It's just. There's other ways to look at this that make a lot more sense. But anyway, as the universe cooled, symmetry breaking released these two genies from one bottle. The weak force took over control of the nuclei of the atoms, and the strength determined the properties of matter. At the same time, the electromagnetic force became master of long-range connections between matter located everywhere in space. Electromagnetism communicates over great distance by means of massless particles called photons, or it involves waves depending on which picture one prefers, and that they may depend on the given experiment. Electromagnetism is also inherently weak, which is why we require enormous radio telescopes or large optical mirrors to gather faint whispers of radio or light energy from the depths of space. I don't know what he means about that. It's not relatively weak. It's what is it, like 40 billion times stronger than gravity or something? But what is the mechanism that allows the electromagnetic force to be sensed over great astronomical distances? And why is it the weak force? Its twin only sensed over nuclear scales. Here, the picture known as the Feynman Diagram shown in Figure 10.1 helps the imagination. Consider a simple case of two electrons approaching one another. Like charges repel, so they will shy away from one another. But how do they do so? Feynman asked us to imagine that when the two electrons approach each other, one of them emits a particle, a photon, which then heads toward the other electron. When the photon is emitted, it gives the electron a kick backward, so to cause the first electron to swerve away from the other. This relates to a fundamental discovery by Newton that an action always causes an equal and opposite reaction. When the photon strikes the other electron, it is absorbed and causes the second electron to change its direction of motion. The particle that carries the force is called a virtual photon because it cannot be seen by the observer, though through its influence, it appears as if the two electrons are avoiding each other. The continual exchange of virtual photons determines the trajectory of an electron relative to one another. The force invoked to describe this avoidance interaction is an aspect of electromagnetism. Feynman's model suggests that the force is carried by photons, which are massless. The force behaves as if a virtual photon is exchanged in the process of electrons repelling one another. There's all kinds of problems with that. How do you have mass, you have a masslessness, but you have inertia at the same time, and they also use this for attraction. And so you can't use it for attraction. It's like the model QED, quantum electrodynamics, began to gain foothold in 1950 and was found to be a very elegant way for describing the action of electromagnetic forces. Field theory, although still useful as a mathematical tool, then lost much of its power. At this point, it is worth quoting Feynman, who cautions us that the way we have to describe nature is generally incomprehensible to us. In other words, as we delve deeper into nature's secrets, we do find answers, but those answers are not necessarily in a form that is readily comprehensible in terms of everyday language. That is why mathematics is not a common language like French, Japanese, or English. It is, among other things, the language of physics. Once the efforts of the physicists to interpret what had been found in terms of common language failed, they were forced into the realm of what was not at all obvious or intuitive. But whoever expected that evolving concepts of nature's mechanisms would remain in the realm of human intuition? Okay, so you got a superior intellect. A Feynman diagram can be used. I know what I'm talking about is you have a superior intellect that created this thing, not that's discovering it. I mean, in a sense, you could say these guys are they have superior IQs, but they're discovering something that's way beyond. It's way beyond the comprehension of humanity. In order, its origins are not fathomable. Okay, the Feynman diagram can be used to show how we see a distant star. The surface of a star emits countless photons that traverse space and strike our eye. The A massless particle could have traveled from the very edge of space-time before striking our retina. Because they are massless, they can travel forever without losing energy through close encounters with matter that would otherwise drain their energy. Of course, if a photon were to strike something on the way here, such as a planet or a dust particle in interstellar space, it would be absorbed and we would never see it. But since space is very empty, most of the photons get through and bring messages to Earth about distant galaxies and early universe. In the case of the weak force, a similar phenomena happens. Interactions at the nuclear level occur over a very short range, and it was predicted that the particle that carries the weak force, the analogy to the photon, had to be very massive, which would explain why it didn't get very far before it ran out of steam. Okay, let me see. I think he means before it collided with something. Anyways, such particles called bosons were discovered experimentally in 1983. That earned Carlo Rubbia, the leader of the team that did so, a Nobel Prize. Now consider the other two forces of the basic quartet. The strong force also involves exchange particles. The carrier of the strong force is called the gluon. The hypothetical glue holding atoms nuclei together. It is heavier still, which means that the strong force can act only over very short distances. Similarly, it is hypothesized that particles called gravitons play a particular role in holding matter together. In other words, what holds you against the Earth is a continual exchange of gravitons between your body and the planet. Well, see, that should push you off the planet. It shouldn't pull you to the planet. However, gravitons have yet to be observed directly. In summary, we can imagine fields as involving the exchange of particles that carry force. The bosons involved in the weak force are so heavy they cannot travel very far. That sets a limit on their action to dimensions of the atomic nucleus. The boson's counterpart, the photon, carries the electromagnetic force. The photon is massless and is capable of traveling across the universe without interacting with matter. That is why we can see galaxies located at a distance vast 10 billion light years. These two forces are the two sides of what was originally electroweak force. When the symmetry was broken, bosons and photons became part of the vast realm of possibilities that define our physical universe. Now we return to a Kantian view that the forces of nature are part of some overall unity. The unification of the forces, the linking of gravity and electromagnetism, was a subject dear to Albert Einstein's heart. The challenge to unify all four forces under a single umbrella has attracted many famous physicists. Cranks and pseudoscientists are also drawn to the subject. Like moths to a flame, for some reason, the temptation of finding a unified field theory has the power to lure rational and irrational minds with equal force. The original goal in the search for a unified field model was to link gravity and electromagnetism in one fell swoop. It was considered to be the holy grail of physics, and many knights in shining armor ride large research grants in the quest for the answer. The path to success is now visible. The strong nuclear force is not part of our direct experience. The force acts as a powerful glue in atomic nuclei and extremely strong at very short distances, but it is not felt beyond the nuclei. And you know, you put a Feynman diagram on it. There were things, if the electrons repel each other because of an exchange particle, then the photon and the electron should be repelling each other too. There's also an exchange particle involved. We have seen that electricity and magnetism are subsumed under electromagnetism in one force, and have noted that under the high energy conditions found in the early universe or in a particle accelerator, electromagnetism and the weak force behave as one. The electric weak force. In following the path toward a fuller understanding of how the other forces are linked to these strong nuclear force and gravity, we rejoin the trail at the point where the electric weak force is in a state of symmetry, when the universe was less than 10 to the minus 12 seconds old. Extrapolating even further back in time, back to a condition when the universe was more compressed and far hotter, physicists discovered that their questions showed that a new type of symmetry played a role. The electric weak force is apparently the twin of the strong force under the extreme conditions that existed when the universe was less than about 10 to the minus 38 seconds old. They were one. This short time span is incomprehensible to our minds, yet it was important in the evolution of the universe. In the brief interval after the universe came into existence in the Big Bang, the electric weak and the strong forces were part of a symmetrical whole, a higher order symmetry. Physicists have described this state under the umbrella of GUT's grand unified theories. At an age of 10 to the minus 38 seconds, the universe was only 10 to the 33 centimeters in size. Okay, well, what about the Pauli exclusion principle? What about, there's so many reasons that you couldn't get there, but anyways. Before that moment, there were only two forces present, gravity and another that contained within it the seeds for the strong and weak electromagnetic forces. To explain this, physicists invoke a state of greater symmetry, known as supersymmetry, that existed in a multi-dimensional universe that must have existed when it all began. Well, if you're going to have a multi-dimensional pre-existing universe, you don't need a singularity. In order to account for supersymmetry, many more dimensions than the three space and one time at which we are accustomed to in our lives are required. The ultimate parent apple representing nature's basic forces may have existed in a universe with perhaps 26 or 10 dimensions, according to two out of a variety of current theories that have yet to withstand the test of time themselves. But this is the thing, this always bugs me about them. Why are you curling them dimensions up? What gives you that right? Why aren't they the ones that are spatially extended or infinitely extended? I got a problem. Okay, anyway. Okay. A theory of everything would allow all forces to be accounted for in a single model and will provide a broad description of the origin and the evolution of matter, galaxies, stars, planets, all which emerged after the hierarchy of symmetry breaking was complete. This may well lead to a theory of everything whose compass may include our existence on Earth, given that we may learn to explain the complexities that result from combining simple matter into higher order structures, molecules, cells, organisms in sufficient detail. Perhaps it is only a matter of time for creative intellects which have emerged out of the sea of matter and forces that constitute our universe to find the explanation. The point of touching so briefly upon these topics at the frontier of modern physics is to indicate a remarkable implication of the existence of the new theories, that they have been invoked to explain the existence of matter as well as the forces between various forms of matter. For the first time, it appears that humankind, as represented by its physicists, at least is on the brink of understanding everything. This does not mean that the details will be understood, only that the broad picture that underlies our existence will have been revealed. The issue is not whether a complete self-consistent picture of theory ever will emerge in the 1990s, that was 1990s, or in the early part of the 21st century. Instead, it is that a possible resolution of many fundamental questions concerning the physical universe may someday relatively soon be answered by a comprehensive theory. At no previous time in history could this have been claimed with quite the enthusiasm that is now devoted to the quest for the underlying concepts. Ampere, Faraday, Einstein, and many other physicists have always sought to unify their understanding of the forces of nature. None of them succeeded. With the marriage of the electromagnetism and the weak force, the first major step in the unification of the forces basic forces was taken. Final success is only a matter of time. The path toward that unification is visible, and all physicists have to do is to move already systematically and carefully. Today, we live in a universe in which four forces seem to control matter. Now we know that these forces emerged as separate entities when the universe was a microsecond old, thanks to the hierarchy of symmetry breaking. For those readers familiar with some of the concepts of modern cosmology. The time when the forces were unified was before the era of inflation. Inflation began when symmetry was first broken. The British physicist Stephen Hawking has made an optimistic statement about whether the discovery of the theory of everything will be possible. I believe there are grounds for cautious optimism that we may now be near the end of the search for the ultimate laws of nature. Skeptics react to this statement and suggest that people have always thought this, but we are hard-pressed to find historical examples where such a consensus existed about the likelihood of success. As far as our story is concerned, the search for the answer to the question of what is lodestone has led us via the action at a distance through electromagnetic fields, QED, GUTs, and a possible TOE. The answers to many related questions now find common answer in the remarkable properties of the physical universe in which we find ourselves. It is awesome to confront the fact that the human brain, by asking questions, has found answers. These answers work so well that we are left with the stunning awareness that we live in a universe in which at least one form of consciousness that has emerged that has the capacity to comprehend not only its own existence but its origins as well, and that's not true. Okay, we can't. Okay, see, here's the problem. The origin quest requires extra dimensional revelation. It's not, the answer is not within the visible system. Okay, so let's keep going. This is a fun book. All right, let's see here. Let's see. Okay. All right, where's my starting book? We begin this chapter by suggesting that most what-if questions are fruitless unless we can come up with ways to find answers. Clearly, we have learned a great deal about electricity, magnetism, and electromagnetism, thanks to nature's thoughtful gift of lodestone. If you accept my arguments, you might wonder if, by analogy, it is possible that natural processes exist of which we are oblivious. But this is what if we cannot deal with, at least not as respectable scientists. We have no grounds for framing such questions except by analogy, and analogy have a way of being off the mark. No matter how fascinating the idea may seem, it is best left to science fiction for elucidation. We can only deal with what we know exists, with phenomena and processes that we can detect and measure. Now, this is interesting because the pre-existing conditions are not, they're not, in a sense, of this nature. the nature we exist in the universe, the pre-existing conditions are not of this nature. So you're not going to be able to close that circle. It's like to understand something. What does it mean to understand something? Well, you compare it to something else that's already known. The best thing we can do with the origins of the universe is from what we do know is that it was designed by God, an intellectual being. That's the only clue. Once you start getting into things like laws of physics and so forth, they don't lead to that. They're not going to lead there. Because they're not that kind of thing. They're the kind of thing that requires relating it to something else that's already created, itself being part of the creation. It can only work within that closed system. See, in other words, the kind of scientific reasoning, the materialistic reason, only works within a closed materialist system, which itself has no explanation for its existence. Why should it exist? There's no reason for it to exist. Today, the search of the Z-Man effect at 21 centimeters continues at the Hat Creek Radio Observatory of the University of California in Berkeley, where Carl Heiles and his colleagues have amassed thousands of hours of observations to detect fields in the Milky Way and at the National Radio Observatories in Green Bank, where I map the magnetic field patterns in a small area of the sky. Interstellar fields of a few microgauss are now routinely detected. Apparently, this is the strength of the average field between the stars. It is typically up to 10 microgauss in vast filamentary tentacles of gas and dust that weave their way throughout the galaxy. These fields are probably just strong enough to account for the alignment of interstellar dust grains. This is interesting. Now he's going to get that. Now I'm going to give this author some more credit because he's actually going to open his mind to the possibilities of the electric universe theory, and so he gets a lot of credit for that. These interstellar fields, they're a lot stronger in some places, and they're strong enough that they form plasma focus devices of the strength which can create a star in a sense of form a star. Shown that moving magnetic fields drive currents, the Oersted discovery that currents moving electrons create magnetic fields. Since interstellar space is filled with electrically charged matter in constant motion, wouldn't we expect those currents to create fields? Indeed they do. But if the fields also move about, would that not create new currents which would create fields, etc., ad infinitum? This endless loop may hold the key to explaining magnetism in and between stars. Once a field is created in an ionized medium, such as in the core of a star or in space between stars, the field maintains itself because of this endless interplay between current and field. Provided no energy is lost, the dance can continue indefinitely. Within the gas clouds in space, magnetic fields become frozen in. That is, they are part of the cloud. If this gas moves, the field moves with it, and vice versa. If the cloud contracts, the field will become stronger and can actually stop the contraction because fields do not like to be crowded. Well, see, now this is where he's a little bit wrong. Understanding this interplay between gas fields forms a science called magnetic hydrodynamics. But the thing is, there are field constructions that do contract extremely tight in some kind of like a Birkeland card. It wraps around itself. Matsuo Tsubo, Makoto, Inou, and other radio astronomers at Nobiyama Radio Observatory in Japan have made a specialty of studying radio polarization near the center of our Milky Way galaxy and found what appears to be a magnetic jet emerging from the center. Yoshiki Sofu of the Institute of Astronomy at Tokyo University is one of a growing band of researchers who believe that this is evidence for a primeval origin of the magnetic field. The ancient field was wound up as the galaxy rotated and is now concentrated near the galactic center where it is tightly wound. This might be a magnetic tornado, he says, conjuring up a poetic image of an enormous swirl of magnetic fields in the very heart of the galaxy. Now, did the galaxy wind it up, or did it wind up the galaxy? Is that part of the formation? Perhaps pulsars are peculiar objects, neutron stars that are remains of cataclysmic stellar explosions called supernovae. Pulsars transmit a stream of incredibly regular pulses of radio energy, which astronomers on the Earth have been studying for over 2 decades. Those pulses provide marvelous tool for studying magnetic fields in space, fields that have absolutely nothing to do with the pulsars themselves. In fact, the technique would work even if we had no idea what a pulsar is. Okay, there's a problem with pulsars. There's a big problem with pulsars. I can't believe. All right, think about this. You have it's crazy because I guess the only way the only way their model would work, the star would have to be spinning in two directions. Okay, it would have to have two axes, and it'd be spinning on both axes. So it'd be spinning around like this and around like that at the same time. Because if you're going to get that kind of radio signal and it's just spinning in one direction, you're not going to get that kind of, it's going to be steady. Or you're not going to have anything. If it's coming from the equator, you're not going to have anything. It's got to come from a pole, and if it's coming from a pole, it's going to be steady. You got to have the pole spinning. It's like, wait a minute, I don't know if you can have a pole spinning like that. And the whole thing, I mean, it's it's supposed to be going faster than a dentist drill and all this. It's just, there's better explanations. The electric universe has much better explanations for it's kind of. An official at one of the nation's primary sources of funding for astronomical research told me recently that if I wrote a grant proposal, I should try to avoid references to magnetic fields in interstellar space in this case, because the referees had habit of rejecting any proposal that deigned to mention the topic. So that's great. That's that little statement there. A little bit of honesty in a universe of hypocrisy. Okay, let's see here. Let's see. And it's with the electric universe guys, Thunderbolts. They're up against that all the time. The dogmatism. Okay, I got a special note on page 229, but we're up to 205. The answer to Marconi's question about how far Hertzian waves could travel is quite extraordinary. The cosmic microwave background radiations travel through all time and space we now receive as radio waves began their journey as light. The waves have traveled since the beginning of time, or at least from so close to the beginning that it makes little difference as seen from a cosmic perspective. The CMB defines how far we can ever see into space. At this point, some readers may recall reading or hearing about new telescopes that are claimed to allow us to see further into space than others that have gone before. Those reports were nonsense. New optical telescopes may see farther in the visible light part of the spectrum than before, but they will never see as far as radio and infrared telescopes have already done. Radio telescopes in particular have been able to observe to the edge of space-time, the beginning of the universe, since 1959, even if the phenomena was only recognized in 1965. Had the mirror of the Hubble Space Telescope been perfect, it would not have been able to see further into space than observers of the CMB have already done. This is because there is nothing to see beyond the cosmic photosphere, and it surrounds us just as we cannot see into the sun through the photosphere unless we use particles called neutrinos, which is another story. For about a century we have been certain that we live in a universe populated by galaxies. Once upon a time, these galaxies must have been formed from vast clouds of matter that were created in the Big Bang. Therefore, if you want to study the clouds of matter out of which galaxies formed, all you need to do is look far enough into space, back in time to an epoch before galaxy formation occurred, and see what can be seen. Well, actually, they haven't been able to do that. Anytime to do, because this book is, I think the book was written, it's a little bit older. I mean, it does have a barcode on it. Let me see, 1993. Okay, well, there's been deeper probes, and they'll just keep it a long exposure on what looked like a blank piece of space and this, like, masses and masses of galaxies, and they're all formed properly. They're not, it's not like these proto-galaxies that they claim. Okay, so I'm going to keep going because we're going to get something really interesting. on page 220, we were to 206, within a few months of the launch of the COBE, C-O-B-E, the principal investigators, John Mather, Michael Hauser, George Smoot, announced the first results. The temperature of the CMB, the cosmic oven, is 2.735 Kelvin, and its spectrum has a shape in perfect accord with the theory of how the radiation was produced in the cosmic photosphere. At the time this is being written, the COBE data show the CMB to be smoothed down to levels of a few 10,000ths of a percent, which possess enormous problems for the theories of galaxy formation and Big Bang universe. No one yet knows the answer to the mysteries of galaxy formation. There is an alternative school of thought by Halton Arp, Sir Fred Hoyle, Geoffrey Burbridge, who have suggested that the CMB is not what we think it is, and that the universe did not begin with the Big Bang. Theirs is a highly controversial point of view, which involves returning to a model in which the universe is a steady state. According to them, the smoothness of the CMB is telling us that it originated very close to the sun and by a totally different process. Yeah, I think they're probably right. Okay. This is called an error of creativity, this chapter. It seems highly likely that humankind, 400 years after setting aside superstition and a mere 200 years from the time that experimentation began in earnest, confronts the possibility that many of the basic questions that have for so long been asked of nature have already been answered. Humankind may be standing on the brink of knowing all there is to know about the broad aspects of nature, in particular about the forces that act upon physical, chemical, and very soon biological systems that, at least to levels of detail that make a difference in everyday life. I want to stress that it makes no difference to our discussion whether we consider the state of final understanding to be very near or 100 or 1,000 years in the future. The point is to recognize that progress in the quest for knowledge has been extraordinary, especially during the 20th century. Now it may be time to ask, what next? What will curious humans do when the answers to their fundamental questions have been found? If you do not believe we will ever approach a time of full understanding of the fundamental issues, why do we bother to continue in our quest for knowledge? The human mind has made enormous strides toward understanding the nature of the physical universe, and in time the biological realms of existence will reach a similar level. Isn't that what we have asked for as a scientifically oriented society that wishes to understand the nature of existence? But once we have found it, what is then left to be done? Well, the thing is, it's not going to explain the nature of existence because it's relative to what already exists. So it doesn't go beyond that closed circle. Like I'm saying, you got to get special revelation for that. Answers may range from solving social and psychological ills to bettering the lot of all human beings and so on. And that is the point. This is great. This guy's pretty optimistic. Look what we're doing now. In 2021, we're about to, go into this new paradigm of a super race, and everybody else is useless eaters and, confined to the pod, and no human relations. You keep a mask on your face so you can't, interact with people, and you've been reduced to to animals, and you're going to eat insects and live in a pod. So that doesn't sound like progress. All right. Okay, now it's time to ask what next. Okay, the human mind has made enormous strides. Answers may range from solving social and psychological ills. The curious human mind and its persistent questioning appears to be approaching the boundaries of the physical universe on all scales and all directions of thought. Once we understand the nature of matter and all the forces that act upon it, we will no longer ask traditional questions. The most fundamental ones, such as what is light, what is heat, what is gravity, what is magnetism, will all have been answered. That's not true. They've just been compared to other phenomena. Richard Dawkins made this point in his treatise on evolution. He points out that the mystery of human existence is solved. Similarly, the mystery of magnetism is solved. In fact, given the depth of understanding of the four basic forces of the universe, the broad picture lies spread out before us. Details may still be explored, but that is not what concerns us. How can we say that the mystery of magnetism is solved? Well, we have seen that magnetism is produced by electricity in motion, and that magnetism is one aspect of electromagnetism, which in turn is one aspect of the electric weak force. There's every indication that this is an aspect of another force described by the grand unified theory. Our search for answers to basic questions in diverse fields of human experience, and specifically of physics, has led us to an increasingly intimate view of the underlying unity of nature, just as Kant suspected it would. This brings us again to the question related to the origin of and evolution of life. Despite continual brushes with religious fundamentalists whose beliefs are deeply threatened by the notion of evolution, biologists have plunged ahead and built upon what they've discovered. You know, there's nothing to build upon evolution. Actually, you could the theory could not exist, and you could continue to make all the progress that has been made. It's a superfluous vestigial of nonsense. That's how, and that's true. You could do. It's just like, look, if nobody had a TV or newspaper or the government, that there would be no pandemic. Okay. The Genome Project. Okay, I'm reading an article about the guy who does the Genome Project. That was heading that up. Francis somebody. Anyways, this is a major step towards fully understanding of the gene, and that in turn is a precursor to being able to find practical uses for such knowledge in the biological sciences. We may stand at an awesome threshold, not unlike that which confronted students of electricity and magnetism in the 1800s. With progress, we learn to design better experiments to search for clearer answers. Inevitably, progress grows more rapid. From this perspective, we must confront the possibility that our species will, before long, have learned to understand the essential issues involved. After all, the universe is finite, and physical phenomena proceed according to only a small number of identifiable laws. Okay, we just mentioned there. Okay, if it is finite, that means its origin is not within itself. Okay. When exploration, I think this is where I got, no, I'm not there yet. Okay. When exploration in the realm of physics began in earnest, complete understanding was not far in the future, at least not as measured on a timescale of human civilization. Will it be any less rapid for the biological and inevitably the social and psychological sciences? Will the rapid exploitation of discovery in the practical realm in those disciplines be any less dramatic than was the invention of the electric generator and the dynamo? For example, the Genome Project, when complete, will allow the microbiologist direct access into every aspect of the human gene. Once the DNA has been mapped, there may be no holding back. Why even consider holding back? Except to avoid the dangers inherent if we consider that our species may be too young to play with these things. Like a child that plays with matches, we face unknown dangers as we discover the answers to our questions. Curiosity has taken us this far and continues to drive us on, sometimes far too rapidly for comfort. Is there any reason to think that our collective curiosity will fade? On the other hand, how much further can we go? Can we learn to live comfortably, all of us, with the knowledge that promises to overwhelm us? Or will vast segments of the population remain ignorant about what is now being discovered in laboratories around the world? Wise people of all ages have suspected that something like this might happen, that hell on earth would befall those who ate of the apple of knowledge. The relative mental pace that may once have accompanied ignorance is gone forever. Our species grows ever more uncomfortable with its vast accumulation of data and knowledge. Is this what it means to leave the Garden of Eden, where once we dreamed and dwelt in mythological bliss? That's another pretty good paragraph, and we see what's going on. Okay, so what you want to do, I'll probably put it on my Facebook. You go to Odyssey and look up the guy's name's Jay Wild, his username, and he does this series called Clown World. And look at his latest Clown World. I think it's Clown World number 15. You look at them all, they're all really good. Look at the latest one. It's just right what this guy's talking about. Already we are forced to ask this as we face the disastrous consequences of rapid technological process that are embodied in the unrestricted exploitation of the planet's resources. Blindly and unconsciously we destroy the ozone layer, threaten a greenhouse catastrophe, another, false science, pollute the oceans and rivers of the planet. Well, that we're doing to some degree, and we're backing off quite a bit. Overwhelm the ecosystems with billions of additional human beings. Well, I don't think that's what's overwhelming it. And they're not, it's just not smart. It's just not smart development. They're not doing it. And I don't mean smart in the new sense of, the interwebs. I mean, intelligent, planned out, well thought out, conservative measures. Anyway, our species already must confront how it wishes to survive in the future, but is it capable of doing so without making conscious decisions regarding the future? At the time these sentences were written, Iraq was found to have been constructing a nuclear weapon. And so even they're picking on Iran even back then. Gee whiz. The cynic may claim that is an example of where our scientific knowledge leads, but I'm trying to project past an age where regional powers struggle to control neighbors, where our collective consciousness has evolved to a level where human beings recognize that we are one species, which is actually contrary to the teachings of Jesus. Jesus says you must be born again. You have to enter that eternal species. In our scenario, archaic edifices of belief will crumble into dust because they will be unable to resist the advance of knowledge. They will fade into obscurity. It may take hundreds, if not thousands of years for this to happen. Yeah, because they see it ain't happening. But surely it is inevitable. I think that personal rationalizations for the existence in terms of expressing a God's will, for example, will inexorably die away. But old habits do not die easily. Well, you know what? The God hypothesis is the only really meaningful one. So how can you kill meaning? All right, am I up to the page yet? No, there's a special page I wanted to. Okay. In the not too distant future, the human species will have to ask what it wants to do next. Someday we will graduate from that school we currently attend, the one in which we study nature. After graduation, we'll have to create larger roles to play. Whether we succeed or fail in that upcoming adventure is up to each of us. But is this likely to happen soon? It seems unlikely because the planet is far from united in regards to how to approach nature's truths. The error being imagined here can only dawn when we have the error, and it probably is an error, but the era being imagined here can only dawn when we have evolved completely out of the age of superstition, a time that may still be far in the future. The trouble is that individually, and certainly collectively, it is difficult to let go of cherished beliefs. However, as many people now warn, potential ecological catastrophe may force us to face the issue if we wish to survive. It remains to be seen whether we will be able to transcend the beliefs that bind and that separate cultures. Well, why would you want to do that? Why not let people be free to believe what they want? Why is this guy such a control freak? The most awesome fact may be that human brain has emerged from the conjuring of evolution to the point where it has learned to comprehend its own existence, to fit together so much of the jigsaw puzzle of the world. Despite cries of caution that we cannot fully know our origins, it appears that we are well along the path toward a profound and perhaps even complete description of our universe and life on Earth. If this is so, before long, we will cease to ask traditional questions. They will have been answered. Our species may be confronting the dawning of an era of creativity, an era during which the human species will have to decide what it wishes to do for eternity, right here on Earth, not in some imaginary world hereafter, not in a space colony, not on Mars, but right here. Our species, as we learn the most intimate secrets of the universe and everything in it, will surely begin to create, in a sense, our grandchildren's grandchildren, who knows how many generations removed, may yet become as gods on this planet, with the power to determine what to do next. Okay, power to determine what to do next. Have become of God, and this is really getting kind of creepy. And how do we get there? But where will that future lie? Has our species evolved far enough in the psychological and social realm to make use of, in creative ways, of the enormous fund of knowledge it has already gleaned from its explorations of the physical and biological realms? Or are we precariously poised with one foot in the error of superstition, the other in the error of understanding? Okay, this is pretty interesting. So see, this is the kind of thing you pick up. Okay, you pick up a book on magnetism, and next thing you know, you're being indoctrinated with New World Order. The story of magnetism illustrates the expression of this syndrome. The pattern of progress can be recognized in the study of astronomy, biology, meteorology, geology, electricity, and other areas of curiosity that were once haunted by supernatural entities. This is particularly true of astronomy, where a gaggle of gods was once believed to control the motions of the stars, sun, and planets. It was true in geology, where the rumblings and upheavals of the earth were the work of powerful spirits. It was so in biology, where such spirits breathed life into inanimate matter to bring us into existence. And in electrical phenomena, what god was more powerful than Jupiter, tossing about bashing of lightning bolts? And that's interesting. He brings that up because there's all this evidence. Thunderbolts Project. You have these, discharge wars between the planets, sort of. And it got much more. There's much more evidence for that interpretation than anything else. We can now look back from our safe perspective in time to recognize that the invocation of gods reflected only the most primitive attempts to explain nature's phenomena. This need to create a model appears almost instinctive. The creation of an imaginary analog, a model of some aspect of reality, represents the mind's need to believe it is in control. I'm unaware that societies or groups of individuals who resort to the beliefs to guide them would invoke images of chaos and confusion, which is what the universe, to a major extent, is really like. Tornadoes do not respond to prayer. Hurricanes are not swayed by offers of sacrifices. Stars explode whether or not surrounding planets are inhabited by sentient beings. Entire galaxies are torn asunder by cosmic violence. No matter how many inhabited planets may dwell in their realm, earthquakes wreak the damage, ignorant of the quota of miracles that allow certain individuals to survive a near disaster while a neighbor is crushed by falling debris. The universe is a frightfully vast and violent place, and individual human beings as an infinitesimal speck in the cosmos. So, okay, there's a lot of assumptions there. This guy's making an awful lot of assumptions. To succeed as an explanation, a model for some aspect of reality must appear reasonable and comprehensible. That is why the earliest models for natural phenomena involved superstitions or myths that were derived from the simplistic concepts that could apprehend by the generations who formulated these explanations. This relates to the Jungian concept of the existence of a collective unconscious to which our myths resonate. that is why today's models for reality are modern explanations for phenomena such as lightning or magnetism would be incomprehensible to the ancients. Scientific discoveries about the nature of physical reality find no resonance with our psychic depths. Why should they? Instead, what we have found at its deepest roots defies intuition. Yet we appear to be able to appreciate the nature of our universe, even if it is unlike anything we might have expected to find. It certainly is unlike anything that any ancient belief system could have foretold. Well, see, I think he's going to find out in the long run he is wrong in the sense that the ancients had a much better understanding of spirituality. And so the quest goes on. Our fund of concepts and language itself has evolved so we can deal with the nature of the phenomena that lie at the root of the truth we seek. Above all, the human mind learned to make models of reality, models that could be tested against that reality. Sometimes a model may involve a real physical simulation of a phenomenon. Thus, a powerful electrical generator can be used to produce controlled lightning. It can be used to create a model lightning flash. And what better example of the value of a model of humankind's approach to truth than the modern picture of the atom, forming a reasonable, correct idea of the atom and of the physics of its behavior allowed a hydrogen bomb, a small-scale version of a star, to be built. Well, I don't know if that's the correct interpretation of what a star is. The fact that the bomb worked meant that scientists understood one of nature's great secrets well enough, had formed an accurate enough model of the structure of matter to make the bomb explode. The measure of a success of a model rests in what we can do with it. Does it allow us to mimic nature, or is it merely a figment of our imagination? Okay. Oh boy, I got another one without... I don't have a starting point on this one. Let me see. Okay, let me see here. It can be argued that focus now on much of science may concern itself with the details involved in getting even closer to the truth. This suggests that in the not too distant future, the desire to get closer to what is already at our fingertips may be of interest only to the experts if we are not already there in some of the physical sciences. A version of this point of view has been argued by Harwood in regard to astronomy. The comments apply to sciences other than physics. For example, biologists are very close to understanding the broad basis of life. This can be seen in the way they manipulate its building blocks. Genes and DNA molecules, fiddling with the stuff of life is only possible if one already has a very good model, one that is close to the way things really are. How close are we to the truth can only be measured by the extent which we can simulate natural phenomena under controlled conditions. Whether in the laboratory and theoretical calculations in the past, a new concept might have altered the way we understood magnetism or electricity, and thus progress was made. But not until the late 19th and 20th centuries did the models become such good approximations of reality that we gained the power to use knowledge gained from experiments to exploit the secrets of nature that allowed the invention of electric generators, motors, for example. The message of scientific progress in the late 20th century is that there is very little that scientists cannot already do, or at least conceive of doing, in relatively near future. Their models, their approximations to reality are working. Curiosity has inexorably led the explorers to approach very closely the nature of truth. In many areas, inquiry in astronomy, physics, chemistry, biology, geology is what we plan to do with this knowledge in the next millennium that should concern us, as we suggested before. Okay, let's see. Success in uncovering that truth and understanding its meaning is a measure of progress, although progress is only meaningful if it brings us closer to understanding the way things are. Not all experiments in the quest for answers lead to immediate success. We hope that success experiment bring us closer to truth. Whether we are getting closer can only be measured by how well we can simulate reality. In science, the judge of this progress is experience. We know we are making progress when the pieces of the jigsaw of existence begin to fit together meaningfully enough to allow us to recognize the picture and use what has been learned to move ever closer to the underlying truth we seek. We know we are closer to truth when we use what we picture reveals to build our own version of the image, the model, and find that it can be made very much like the original. It's the image builders. Okay. All right. There was a passage in here. I guess I'll go back to it, but let me finish here. Okay, let me see. The error of superstition. During this error, okay, so this guy breaks down. He's sort of got a systematic epistemology. From superstition to uncertainty, grasping at reality, from discovery to primary paradigm, parting the ways approaching the truth, age of creativity. During the era of merging human minds, seeks succor in a superstition in its quest for answers. Initial explanations of natural phenomena usually reflect fear of the unknown. To the primitive mind, many, if not all, natural phenomena appeared magical. The existence of lodestone, a naturally occurring magnetic form of iron ore, fell into this category. The lodestone was magical because it attracted other pieces of iron over a distance and did not require the intervention of any physical agent to establish the connection. Considering as another example the fact that in ancient times the motions of heavenly bodies were believed to be caused by the action of many different gods. The Egyptian god Ra, the sun, was believed to sail across the sky in a boat. In many primitive cultures, each of the planets was associated with its god, a fantasy that continues to enrapture astrologers. Similarly, both static electricity caused by rubbing amber and a strange property of lodestones, which we now call magnetism, were thought to indicate that souls inhabited these objects. Other natural phenomena such as lightning and thunder expressed the action, while usually wrath of specific gods in societies. Such deities are still believed to be in control of natural phenomena, including the origin of life. It is not surprising that many superstitions, in particular those involving one or more gods, were invoked to deal with terror that filled primitive hearts and minds in confronting the unknown. Well, the problem here is that this is all relative in the closed circle, and that in order to get to the actual source of the closed circle, you have to be willing to receive information from above. Phase 5, approaching the truth. Ever since Einstein realized that relativist concepts were of consequence in the observable universe, a great deal of effort was put into the search for underlying unifying principles that would link the four basic forces of the universe. One of these forces is electromagnetism, the product of the wedding of electricity and magnetism with a strong dose of time thrown in for good measure. By the late 1960s, physicists made more progress towards synthesis, so that now we find that electromagnetism has in turn been wedded to the weak force. In the electroweak theory, a paradigm shift occurred that involved a unified field theory. It now appears that only time is required to spell out the details. Looming on the horizon is the theory of everything whose nature is hinted at in the studies of fundamental particle physics and cosmology. Phase 6 lies in the future, and its details cannot be predicted. It is likely to involve a vast and broad synthesis with other realms of human curiosity. This will surely bring to the fore human creativity as our species makes rational and constructive use of all knowledge gained through centuries of scientific exploration. It will be a time to ask what we will want to do with our knowledge. How this question is answered remains to be seen. I could construct a complex table to show how several sub-branches of various sciences must inevitably trace their own paths through these phases of progress. For example, with the discovery of radio waves and the subsequent development of radio technology came the fortuitous discovery by Carl Jansky in 1933 that the Milky Way was a source of radio waves. While this discovery could be said to have occurred in Phase 3, Stage 9, elucidation of theory, or Phase 4, parting of the ways, of the study of electricity and magnetism, the subject of radio astronomy itself, was born into its own version in Phase 1, Stage 3, an era of uncertainty. Skipping, we will admit the terrible throes of superstition. During the first decade or so of radio astronomy, its practitioners dwelled in a world of uncertainty because no one had any idea of why astronomical objects emitted radio waves. It required the invention of better and more sophisticated equipment, Phase 2, Stage 4, which included the world's largest radio telescope in the United States, Australia, and Great Britain, before the era of discovery well and truly began in the 1960s. Today, much of this discipline is no more or less than a part of the larger subject of astronomy. Any future paradigm shifts are likely involve the most fundamental questions. For example, those concerning cosmological issues related to the origin and evolution of the universe. Is space really expanding away from the minute point that defined the Big Bang, the current paradigm, or is some other explanation needed to account for the many peculiarities that still stand in the way of intellectually satisfying synthesis? When one looks too closely at any one branch of science or its subdisciplines, the boundaries between the phases of progress will blur and disappear. As an exercise in imagination, you are invited to decide for yourself where other sciences and pseudosciences may be placed in the spectrum of progress. For example, astrology is clearly rooted in an era of superstition and will, by definition of the nature of astrology, forever remain there. But where the sociology, psychology, and economics, but where are these things? Wherever we place them now, there is every hope that with time, these disciplines will move forward to approach their own great synthesis. Every topic of scientific inquiry initiated in ancient times necessarily involves models that today seem primitive, much as a child's view of the world may seem rudimentary and naive compared with that held by most adults. It is hardly surprising that our culturally shared views of the universe, of the nature of the universe, should have been simplistic, especially when we realize that it is only over the last 5,000 years or so that human mind began to question the nature of its own existence. Maybe that's because it hasn't really existed for much longer than that anyhow. There's fundamental questions: Stonehenge, the pyramids, rock paintings, cuneiform script on ancient tablets all attest to this. For humans to discover truth, nature had to be approached directly, but the methodology for doing so through experiment did not emerge until 1600 in the era of Gilbert, Galileo, Kepler. Only then did superstition in many areas of human inquiry begin to be called to account. Inevitably, they fell away, even if for several more centuries the weight of public opinion remained unaffected by the scientists' radical new way of interrogating nature. When we look back on the evolution of the scientific approach to nature's secrets, we recognize that two conditions had to be fulfilled for progress to be made. First, individuals had to be personally interested in the outcome of their quest, and second, their search had to be carried out unhindered by doctrine or authority. The corollary is that whenever a new approach to finding answers threatened the previously held beliefs of large segments of the population, as represented by its religious edifices, for example, progress is impeded. Today, in regard to the important questions about the origin of life and the reasons for existence, large segments of society are still in the grip of superstition and prejudice, even though the study of more physical and benign subjects such as electricity and magnetism have long since broken free from the yokes of belief and wishful thinking. Today we understand magnetism, electricity, and large segments of our world population benefit from higher standard of living thanks to what the pioneers discovered, but those discoveries could be made only as a result of a scientifically rational approach to nature's secrets. And now it's getting the pod and eat the bugs. In 1609, Galileo Galilei turned his new telescope upward and found 4 pinpricks of light near Jupiter, which he realized were moons in orbit about the planets. That meant that one cherished belief that the Earth was the center of all motion was plain wrong. Jupiter was the center of motion for its 4 moons, a shocking discovery for a geocentric clergy. Galileo also saw the phases of Venus, which provided that it orbited the Sun, which proved that it orbited the Sun, and proved those 2 objects were not as perfect as everyone had believed for so long. For very good psychological reasons, Galileo's observations did not go over well with the Church. As the self-appointed and ultimate arbiter of truth, its role was implicitly challenged by Galileo's observations. Yet this man merely reported what he saw, and perhaps that is why the threat was so great. The scientific age would teach us to see more clearly, to perceive new truths that exist whether we want to see them or not. But from the Church's point of view, if Galileo were allowed to report his heresies, where would the rot stop? So, anyways, of course I have problems with that interpretation of events, and of course, the Church is not what they're calling church. There's not the Bible, and I certainly think that you can't get there with the Bible. You could do this, and here's what I would do. Okay, there used to be a 360-day year, right? You had the flood of Noah. What happened during? It's described in the flood that the water there was a landmass, water under it, and that broke open, and the water came up. You have solid now. The solids descending, the liquids coming up. What's that going to do to the rotation of the Earth? What's going to speed it up? That's why you went from a 360-day year to 365. You could also argue that the orbit's probably not elliptical. These catastrophic events. You can make those arguments. Anyway, in seeking answers to questions about the nature of life, we are still in the midst of an upheaval that dwarfs Galileo's struggle with the Church. 150 years after Darwin found evidence for the phenomenon of evolution, we're still witness to religious fundamentalist reactions to scientific explanations about the nature of life. Even in our enlightened age, we find publishers quaking at the notion that local authorities will reject a biological textbook because it mentions evolution. Most scientists are polite about these issues and go out of their way to accommodate beliefs held by millions of people. If we are to be honest in our pursuit of knowledge, we must surely recognize that there is a profound gulf between worldviews founded in belief and those built on experience. Objectivity in our quest for answers requires that we set aside preconceptions and expectations. Like Faraday, we must recognize that we will only find answers by patiently attending nature's school. And it's funny how the polite scientific community is treating those who question the pandemic. The concept of evolution subsequently liberated the inquiring mind from the shackles of ancient beliefs about the nature of existence. And it hasn't done any such thing. As Richard Dawkins writes in his book, The Blind Watchmaker, our own existence once presented the greatest of all mysteries, but it is a mystery no longer because it is solved. This is a remarkable thought, that the essential mystery is understood, but is only solved in the eyes of those who look directly at nature and who are willing to observe the remarkable fruits of human curiosity. I want to persuade the reader, Dawkins continues, not just that Darwinian worldview happens to be true, but that it is the only known theory that could, in principle, solve the mystery of our existence. This most fundamental of all mysteries, the nature of life, is the only known theory, which for thousands of years has been dealt with in terms of superstitions, some of which evolved into religious dogma, remains in the murky depths of myth and metaphor. But ever since human curiosity was brought to bear on the question, in particular as demonstrated in recent progress in molecular biology. The blinders have been pulled back, and scientists have found that a concept of an anthropomorphic interfering God is no longer a sufficient or even necessary cause for any of life's experiences. While individuals may feel or believe that God is involved, the essence of the scientific endeavor is to seek beyond feelings and beliefs, to examine nature of truth, the way things really are upon close and careful inspection and measurement. So, yes. All right, so that's, remember now, this is a book about magnetism. It's supposed to be a science book. So here I think one of the observations I made, and I skipped over, I wanted to talk about was, I was talking about, deep space and looking in deep space. And the idea is you go back so far, and there's this, so you're supposedly, you're looking back towards the beginning of time. It just doesn't make sense because, okay, you had to bring, the Big Bang, you had to bring the material out there. So the material comes out slower than the speed of light. So how are you going to look back? The light would have been gone by a long time ago. Just see, it doesn't add up there. And what about this early epoch? Where you had light only, so to speak. What about Olber's paradox? There's so many difficulties. Now, of course, Olber's paradox is more of a problem for the steady state universe. The Big Bang has a million problems on its own. It doesn't. All right, I don't need to. But anyway, so that's the book and the traction, and one of my main points here is, there's some interest in science there, but it really is the philosophy of science is to point out that how these worldviews, these Marxist worldviews, are interwoven into all kinds of publications and, of course, pop culture and so forth. So I hope that those of you out there who enjoy asking questions about the origin of the universe and cosmology and so forth, found that kind of an interesting little excursion. So I will, of course, I'm making most of my content goes up on Odyssey and not YouTube. I still have the YouTube channel just because I can direct people to Odyssey. I'm going to try to put this up on YouTube. I'll see if they don't take it down for some reason, for hate speech, I guess. So let's see what happens. Anyways, thanks for tuning in. You can look me up on Library. You type in one word, Love and Division, and you should be able to find me there on Odyssey, Library Odyssey. Either way, they're going to keep, you have the library app. That's a good idea. Now, the interesting thing about the library app is that it downloads everything you watch. So when I see something really interesting on Odyssey, I'll open it up in library and have it downloaded. I think, there's probably a way to download it on Odyssey too, but this thing's automatic. I just let it go. Of course, I don't know where to find the downloads, but I'm sure my computer guy will be able to help me with it. All right.